Ice, ice, baby!
In the previous video, we simplified the expression we derived from physico-chemical concepts for the impedance of an electrochemical reaction of a dissolved redox couple under conditions of linear semi-infinite diffusion. For this, we assumed that there is no kinetic hindrance to interfacial electron transfer, so-called Nernstian behavior. We have arrived at these equations for the Warburg impedance and the Warburg coefficient, which takes into account only linear semi-infinite diffusion limitations. For an AC perturbation, this impedance describes concentration oscillations at the electrode propagating into the electrolyte as a damped wave. Due to finite diffusion speed, concentration changes are phase-shifted relative to the alternating current through the electrode. How far these concentration deviations from the DC operating point penetrate the electrolyte depends on the frequency of the perturbation. So, the Warburg element can be conceptualized as a series connection of a frequency-dependent resistor and a capacitive reactance, 1 over omega c, with a frequency-dependent capacitance, although such electrical circuit elements do not exist. Thinking about it in this way is somewhat closer to Emil Warburg's original idea of describing periodic concentration changes at the electrode, which disappear with great distance from the electrode as a capacitance of polarization. As we can see, both the real and the imaginary part depends on the square root of the angular frequency. Further, both impedance components are of equal value, and accordingly plotting in the complex plane gives a straight line with a slope of 1, which we call Warburg line. For slower diffusion, for example due to lower concentrations or smaller diffusion coefficients, the Warburg coefficient becomes larger, and for similar frequencies the magnitude of the Warburg impedance increases. The diffusional impedance approaches 0 when the angular frequency tends towards infinity. To illustrate, at high frequencies there are virtually no concentration changes at the electrode surface or in the solution due to rapid change in reaction direction. In the impedance spectrum of an electrochemical reaction of a redox couple in solution, other influences can also be seen, such as the electrolyte resistance, which causes a shift of the impedance spectrum along the real axis. Fortunately, we can combine the equivalent circuit approach, which is based on electrical elements, with our new element derived from physico-chemical equations. When both electron transfer kinetics and diffusion hindrance are present, diffusion influences may vanish at high frequencies, where interfacial charge transfer predominates, forming a semicircle in the high frequency range. At low frequencies, the diffusion limitation gains more and more influence. A Warburg straight line is observed. Under certain circumstances, it is possible to extrapolate to the real axis intersection of the initial semicircle and thus estimate the exchange current densities of the underlying process. Note that the base point of the straight line on the real axis also depends on the double layer capacitance. The frequency at which the transition between the semicircle and the straight line occurs, or the overlap, depends on the concentration of reactants and products, on the exchange current density and on the overpotential. Remember that we derived an expression for the Warburg impedance which still contained kinetic parameters like heterogeneous rate constants when we considered interfacial electron transfer and linear semi-infinite diffusion. This description of a Faradaic impedance comprises different terms for ZW and RCT than our previous approximation in basics of EIS. It thus offers a broader application and can account for mixed kinetic and transport control. As we have seen in Kathleen's experiment, changing the concentration of the redox couple can affect several features of the impedance spectrum. Today, we will see what happens if we affect the mass transport by rotating the disk we use as working electrode.
Hello and welcome back into the lab. Today we are measuring CVs with the same setup as previously. Again we have a ferro-ferricyanide couple, in this case 5 millimolar each, supported by 50 millimolar sodium perchloride electrolyte. We have the carbon rod as counter electrode, the MSE as the reference electrode, and the working electrode is again the platinum disc. It's mounted to this device. It's a rotator, and we will use the rotation for today's measurements. A CV without rotation is already measured, as you can see here. And now it's time to start the rotation. The rotation rate is 400 RPM. Let's see how it influences a CV measurement. Okay, now we start the measurement. First again OCP. Seems to be stable. Now here is the old CV on top without rotation, and now we can see the one with rotation is measured at the bottom, and we see we don't get a peak, more like a current plateau. Now we are going to the negative region, again getting a plateau, and together it gives us an S shape, or more professional, a modal shape. So it's a bit different if we use this rotation or not. And now I will hand over to Sebastian, who will explain this behavior on the whiteboard.
Alright, now let's have a look at what changed in our experiment. And for this, let's begin by sketching our setup. What we have is our rotating disk electrode. Where we have our electrode down here embedded in a non-conducting polymer. This is our electrode. Now previously, in the case of linear semi-infinite diffusion, we performed our experiment just like that. But now what we've done is we have rotated this setup. So this entire apparatus now rotates with a rotation rate. Now what does that do? First of all, as we rotate this setup, the fluid that is close to the electrode, and this face of the setup, is sort of adhering to the surface via friction. And what this means is, as it rotates, it experiences a force outward and is essentially flung outwards in a radial direction. And as this fluid is flung outwards, further electrolyte rushes in from the bulk to replenish it. And what this means is we now have the case where we have forced convection. So now that we know what effect the rotation has, what does that do to our CV? Now, for this, let's sketch the plot of the concentration over the distance from the electrode. The distance from the electrode, if you recall, we sketched in this direction and called it x, where x equals 0 is at the electrode. And now let's plot the concentration along this direction. And for this I will consider the reduced species. So the reduced species has a bulk concentration. here marked by this dashed line, CR bulk. And now, as we begin to increase the potential, we decrease the concentration of the reduced species at the electrode. And now, as we scan in the forward direction, this concentration further decreases until it finally reaches something approximately 0. And as time moves on, this diffusion layer then extends further and further into the electrolyte. So that in this direction, time increases. So now, what happens if we apply a rotation rate? And for this, let's sketch the same plot over here. We will plot the concentration over the distance from the electrode. And our same bulk concentration, CR bulk. And if you have a look at what this induced forced convection here does, in this plot, what happens is that further electrolyte streams towards the electrode from positive x. So from here, we now get forced convection. And this forced convection brings further bulk solution, bulk electrolyte, towards the electrode, thus replenishing any electrolyte that might have been depleted and the concentrations that may have been reduced. And what this means is that the diffusion layer can no longer extend as far as it once did. In fact, what happens is that, well, we apply a potential and initially the concentration at the electrode decreases as well. But we reach a point where, due to this replenishment of the electrolyte, the diffusion layer can extend no further. So as time increases, what happens is we get a constrained diffusion layer thickness. Let's call this here diffusion . Delta. Now, because this thickness is now constrained and can grow no further, the gradient, the concentration gradient, which determines the flux due to diffusion, is also constrained. And so that means, well, before we had a peak, because, well, the concentration profile extended further and further, and the gradient decreased, and so the diffusion limited current, basically the diffusion current, decreased as well. Now we have a constrained diffusion layer thickness, and we have, therefore, also a constant current. And so this means we run into a current plateau and not a peak. And for our cyclic voltammogram, let's sketch what this means. We again plot current over potential. So, and for this case, let me plot this initially with green for this rotation rate. Instead of a peak that would appear here in the condition of linear semi-infinite diffusion, we run into a current plateau. And in the reverse scan, we get a similar plateau here. Now in this case, I've sketched this for the reduced species. Of course, for the oxidized species, you can also plot such a concentration profile, where, of course, well, if the concentration of the reduced species decreases, the concentration of the oxidized species increases, and so everything is vice versa. Now, if we increase the rotation rate, what this does is it increases the velocity at which bulk electrolyte moves towards the electrode, and this constrains this diffusion diffusion layer even further. So for a higher rotation rate, our limiting diffusion profile may, for example, look something like this, where we now have a smaller delta here. And in that case, because the diffusion layer that we can now achieve is smaller, the gradient is higher, and the current plateau is also higher. And now, let's go and have a look how this phenomenon, this forced convection, affects our electrochemical impedance spectra.
Now we have seen how the rotation of the working electrode influences a cyclovoltammogram, and now we basically do the same thing with an impedance measurement. So we have here again the same setup. Here carbon rods as the counter electrode, MSE marked in blue as reference electrode, and of course the rotating disc electrode, 400 RPM, made out of platinum. The solution, again, ferro-ferricyanide couple. Okay, as always, we start with an open circuit voltage. And now the impedance starts with a real axis offset of around 60 ohms. Again, forming a semicircle with a diameter of around 50 ohms. And this is then transversing to something that looks like a 45-degree line again. We are measuring from 100 kilohertz to 100 millihertz. Now going to low frequency region, we can see that it doesn't keep a 45-degree line, it's leveling off. We already know this is a region where we get the diffusional behavior mostly. So in this case, because we are rotating, we don't have this semi-infinite linear diffusion anymore, and therefore we cannot expect to get a 45-degree line. We get more like a second semicircle instead. At least it looks like this. So if you encounter something that is not a Warburg line, it doesn't mean necessarily that it's not diffusion. So keep that in mind, but the explanation for this is a matter of another video. See you then.